All right. Welcome to this video on Robinson annulation, which is a really wonderful reaction that we didn't have time for in class, which was really sad. So I'm glad you're watching this video. Hopefully this will be educational and helpful for you and for your future careers. Robinson annulation is something that sometimes still is very much used in organic synthesis. It's very classical and versatile reaction that every student of organic chemistry really should know. This is the first year in OChem teaching I've ever done that I didn't get around to actually covering it. So that's kind of sad, but it's there's a typo there. I just want you to know it's a great way to make cyclohexenone with double bonds. So we're talking about this ring. That is formed by Robinson annulation. The word annulation means you make a ring. And I just want you to notice that this ketone or the alkene, they happen to be cyclic structures. They don't need to be. I want you to notice that in the product there's 3 rings because you formed this cyclic system, cyclohexenone. The other 2 rings just happen to be there from the beginning, so that has nothing to do with the reaction. I'm actually showing the exact same condition that Robinson used back in 1937, for which he won a Nobel Prize in 1947. And you might think, well, gee, talk, like, how is this such a great chemistry? It doesn't seem like, it just seems like just any chemistry we learn about. Well, I want you to notice that this tricyclic system has the right skeleton that is almost 3/4 of the way there to make the skeleton for all the steroids. Or steroidal compounds have this tetracyclic system, and they're, steroids are powerful hormones. There was really not a good any way to study or exploit them as potential drug leads back in the day, especially in the 30s and 40s, right? 1900, the 1930s and 40s. And so this was the very first entry into this class of fairly complex structures, and so that's that allowed the study of steroidal compounds, and so that's why the Nobel Prize there. It seems like a really complex reaction, but it's really just 2 reactions in one pot is what we're doing: Michael addition and aldol condensation. And so even just studying this would be a really good review for you to think about the Michael addition reactions and aldol condensation reactions. So how would this work? You need a ketone that can become enolized with a strong base, like this. So sodamide is a really strong base that can do this. And become an enolate. Remember, enolate is a soft nucleophile, and so for that reason it is great at doing 1,4 addition or Michael addition, right? So it's this enolate carbon that is attacking with this electrons. So electrons will be pushed up into the carbonyl, after which so this is the Michael addition. Okay, so we just formed this new bond here, and so that's the Michael addition reaction. Now, that does result in this enolate, and this can do things like this can act as a base as well. So I just want you to know that, like, it could grab a proton from the other alpha proton and sort of tautomerize like so that enolate would be on the other carbon. And there's different ways to show this. Perhaps the way I'm going to show this now might be that just to avoid confusion as much as possible, perhaps we could just reclaim a proton from amine. That might be the least confusing way to show it. I'm not really certain, but this is just a tautomerization reaction. So we just regenerated amide anion that could enolize this. Now, the reason why we're showing that is because this enolate could, I want you to notice this is not the thermodynamic enolate, so it's not really preferred, but at any given time you can have a little bit of this enolate with the nucleophilic carbon being over here. And the reason why that matters is once the nucleophilic enolate is on that end carbon, that enolate can now actually attack this ketone in an intramolecular way, which would be a really fast reaction. And notice that this is an aldol reaction. So that's sort of the second part of this Robinson annulation. Okay, and that's really the product of that first step. Now, after you treat this with acid, especially if you heat this, you could, maybe I'm just gonna skip a couple steps here. So you just have excess acid, let's assume. That alcohol can be protonated, and so could the ketone, and this could tautomerize or become enol, I should say enol, through tautomerization if you grab a proton from the alpha position. This is the same mechanism we went over in aldol condensation reaction that is catalyzed by a strong acid. Oops. You know what? Let me, just to save steps here, let me just have this, oops. This other oxygen, grab it that way. I guess we can save steps, even though technically it's more likely that the solvent water takes up that proton, but saving time and space seems like a worthy goal right now during this busy time of the semester. So we just, this is still a fairly reasonable mechanism. So the enol kicked off that water. The end result, of course, is an elimination reaction. So you end up with this alkene. And if we were to grab that last remaining extra proton, that would be the product. If you rotate this around, hopefully you'll see that that's the same material or product as this structure. So that's the original Robinson annulation reaction. And if you could sort of, this is the dehydration bit. If you could understand this, now you understand Nobel Prize winning chemistry. So if you could have done this back in the 1930s, you would have won the Nobel Prize. So that's pretty amazing to think about. Now, let's think about a couple other examples because this reaction is a little bit hard to master, I think. So, like this here is actually a good Robinson annulation setup. We have an enolizable ketone, okay, and a Michael acceptor, a Michael addition acceptor, 1,4-addition acceptor. So how would this work? This would work through this enolate, doing Michael addition into here, and so you would end up with the intermediate that would look like that. And for this to form a 6-membered ring, this carbon needs to get enolized, and that can happen by equilibrating this enolate. And so that would be certainly the case with fairly mild, I mean, it's still a strong base, but it's not like an LDA type of really strong base. Under this condition, you can end up with equilibrating back and forth, between these two enolates. That is just a tautomerization, and so this could undergo intramolecular aldol condensation. We're going to skip some of the steps here, all right? We should end up with this cyclohexenone product, okay? So just to make sure we're all on the same page, so there's 7 carbons there. That would be like 1, 2, 3, 4, 5, 6, 7 carbons there. Okay, so that would be the Robinson annulation reaction, and again, it's a great way to make cyclohexenone. Okay. Here's a synthesis example. Let's think backwards from the target product, and since we just put this right after the Robinson annulation example, you should be expecting to use Robinson annulation, but you might wonder, well, what's going on, because you don't see cyclohexenone, but you should be able to make this final product from cyclohexenone, and that would be this cyclohexenone, and then we're doing a 1,2 addition of a hydride to reduce to this, right? Like we don't, and remember, lithium aluminum hydride is a very harsh and hard nucleophile, or nucleophile source that is hydride, and so we should be able to reduce that ketone to the corresponding alcohol doing this. And this is a cyclohexenone now, so we should be able to make this via Robinson annulation. One way to dissect this when we're thinking about Robinson annulation is we could make this bond through Michael addition and this bond through aldol condensation. That's basically the idea here, okay? And to do that, we need, apparently we're starting from this ketone, so we could form an enolate selectively with something like LDA. I mean, it doesn't have to be, but I'm just trying to use a variety of examples. And then the Michael acceptor would be this ketone, and follow that up by treating this with strong acid and heat, and that would complete